Okay, Occam's razor says, non sunt multiplicanda entia sine necessitate. Entities are not to be multiplied without necessity. Now, the standard way people usually think of that is simple models are usually better. I'm going to claim that's not a very good translation. And if we actually go back to the kind of the original roots here, entities are not to be multiplied without necessity, I think that is a little bit more meaningful. And so I do want to talk briefly about why and what that has to do with machine learning. Let's do an example that we're slightly familiar with. Suppose this is our space, and we've got some points here. There are some points. Let's build a decision tree. How do you do it? Well, you pick a division. Suppose we were to divide here, and then maybe here, and then there. We'll do one here and there and there. This is one possible decision tree for dividing this particular data. Do you agree? Yeah. Okay. Well, another candidate one would be to continue and divide there and there. We could divide here. We could divide there, there, and there. And we could also divide here, and then there, and then there, and then there, and right here. And at some point, somebody's going to stop me and say, why? What are you doing? Here, and we can do it again there, and we can do it again there, and we can do it again there, and one more time right there. Okay, I'm going to stop. The big question, which model will make better predictions? Come on, you know the answer. Okay, it's obvious. The point is, we think that this one makes better predictions than this one. Why? Because that one's stupid, right? What is so dumb about making superfluous divisions in the tree? Yeah, you're going to have to run a little deeper in the tree, so it's going to slow down your computation. But how do you know it doesn't make better predictions? Well, let me ask this question. Is reality simple or complex? Matter of perspective? Okay, relative to what, right? Okay, is the reality we describe in school sufficient to describe the complexity of the universe? Is the universe more or less complex than that which you have learned at your university? More. Obviously, the universe is far more complex, so doesn't that suggest that truth, reality, is more complex than the models we build from our data, and doesn't that suggest that a more complex model would be better? Yeah, so why isn't a more complex model better? Or is a more complex model better? It is true the universe is complex. It is true that truth is always more complex than we understand, right? I mean, we had Newtonian physics, and it turns out relativity, and we didn't see that coming, right? So were scientists dumb to listen to Newton? No, Newton had the best model yet. Okay, scientists, well, I guess before science, the Earth used to be flat as far as we knew. And then people said, no, the Earth is round. Was that true? Well, no, it's not really round. It's a smushed ellipsoid, right? Except then that model was later refined. It's not really a smushed ellipsoid. It's a smushed ellipsoid that's slightly oblong. And it turns out there's mountains. And it turns out that's not accurate either because there's trees on the mountains and there are footprints in the sand. And if you really dig down, I mean, Google Earth is a pretty accurate model, but it's not done. And if I'm outside and I take one step to the left, technically the topology of the Earth just changed slightly, right? And every time I do push-ups, you can just feel the Earth kind of going up and down on the other side, right? Or at least when Chuck Norris does push-ups, it does. He doesn't do push-ups, he pushes the Earth down. The point is, truth is complex. It really is. But if you make a model that is arbitrarily complex, there are so many possibilities that it's highly improbable you will arbitrarily be correct, right? And in fact, it's exponentially complex with every added variable. Therefore, it turns out that simpler models make better predictions. And that's kind of what people use to describe Occam's razor, except look at this. Entities are not to be multiplied without necessity. That's not quite saying simpler models are better. Let's consider one other model. Here is yet another decision tree. Which decision tree is the best one? We should probably vote. How many people say the one on the right is the best decision tree? No votes. How many people say the one on the far left? We got 1 vote. 2 votes? 1.5? Can't tell if that hand's up or not. We'll say 1 vote, and then everybody else votes for this one, right? Mm-hmm. Okay. Those are awful tally marks. Lots of people think this one's the best. I claim that here's what we know. This one stinks. I don't think anyone can say which of the trees on the left are the best unless we start defining stuff. More specifically, let's make a continuum here. And somewhere along the continuum, we've got what the baseline model predicts, right? And somewhere along the continuum, we've got everything that's justified by the data. And somewhere along the continuum, we have reality. And reality is always more complex than the data because why? We're not omniscient, right? We don't have total awareness of everything in the universe. There is stuff going on that we don't know. Therefore, our data is never a full description of reality. And in fact, the best model would be the universe itself, would it not? And anything short of the universe is insufficient to describe the universe, in theory. So the question we ask here is, where do you want me to place the complexity of our model? Baseline's a pretty simple model, and we know it makes crappy predictions, right? So we probably want to be right of that. We know that reality is too darn complex, and we don't have access to it. This is all the data we have in the universe. This is all the data we've collected, right? If that represents everything we really know, is there any reason to be over here? Entities are not to be multiplied without necessity. This is what I claim is necessity. The data is, hey, we know when our model is not right. In fact, I should label this model. And to multiply entities without necessity is to say, make your model more complex. And Occam's razor really says, without necessity, meaning if you don't have some data to tell you, don't add extra things to your model. And so Occam's razor says, if you're over here, bad, get at least over to here. Is that as far as you should go? I'm going to claim not always. Remember that Arizona problem? Remember the Arizona weather problem where it turns out baseline did the best? In that case, pushing your model way down like that is the best thing to do. And there are other cases where being almost as complex as your data is the right thing to do. So I'm going to say that this area around here is the region of possibly optimal models, where optimal means given the data we have and assuming we can't get any more data and no more about the universe can be known, and this represents everything there is, and lots of other things. And by the way, I just made up that expression. That's not a recognized concept. But all right, there is now. I'll publish it right after class. The best model is the true model. So there is a model that's better than our data shows. But if there were, would you ever know about it? By definition, no, because I just said the data is all we know. Now, sometimes you get in situations where there is subjective data or data that's hard to throw in your data set, or data information that, you know, maybe you have feelings in your heart and they've been accurate a bunch of times. There's lots of reasons why people can say, hey, maybe I have valid justification for making my model more complex than the data says. Is that breaking Occam's razor? I guess that depends on what necessity means. If necessity is just the data you have formalized, then yes, that's breaking Occam's razor. If that includes all the data you have, where it's every possible kind of data, then you should go as much as is justified.
If your data were actually accurate, then the data would be shared.
That is exactly what I'm saying, is if you've got additional information, you should formalize it, right? And that's kind of the principle science is founded upon, is science says, if somebody claims this is true because they're these great authorities and they know a lot, we don't care. If they have some reason for being true, they better formalize it and get it into the data and bring the data up to match the model. Science under no conditions will accept a model that is more complex than the data. And that's an important principle to recognize. A lot of times people will say, hey, we have proof that Occam's razor is bad because here's a real world example, and it turns out reality was more complex than the simplest model that fit to the data. What's their mistake? Well, they're kind of playing games with the definition of data here, because if there was any way to know that at all, then it was in the data. And if there wasn't any way to know that at all, then it turns out that they were guessing and getting lucky, and so that's not the odds of getting lucky are really low. Therefore, according to Occam's razor, the best you can ever get is right here. So Occam's razor says never be in this region, and it makes no claims about where to be in this possibly optimal models region. You know, if you want to make, instead of making straight line divisions, can you make diagonal line divisions? Yeah, but then for that matter, can you make hearts? Just because they're beautiful.
Is Valentine's Day?
No. Okay, I'll make what's a good symbol to make for Thanksgiving? How do you draw a turkey? That is not easy.
Technically, yes.
Okay, we could make turkey-shaped divisions around our points, but the thing we would have to justify is why are we doing that? And if the data doesn't say to do it for some reason, why are we doing that? Well, you're violating Occam's razor if you're more complex in the data. So I kind of hammered in what Occam's razor is. Occam's razor doesn't say, keep making your model simpler, technically. Although, should you keep making your model simpler? The answer is maybe. Here's when you should. Is this data, let's go back to this one. Are the reasons why these points are scattered the way they are because of noise or because of truth? Do you see the question I'm asking? Could it be that the reality is there are blue points over here and there are red points down here, and that's the universe that's generating the data, and the reason there happens to be this spurious blue point, I'm even outside of the box. What I mean is, imagine that blue is really centered around here, and red is really centered around here, and we want to say, why is there a blue point over here? And why is there a red point over here? Well, anomalies, noise, stuff happens. Maybe our sensors are bad. Maybe there are unusual cases, right? Imagine if you were measuring the heights of boys and girls. What does your data look like? And yet, chink and chink. How does that happen? Yeah, I mean, some boys are short, some girls are tall. That's okay, right? Does that mean boys and girls are the same size? Yes. Okay, on average, no. The mean of the boys is right here, and the mean of the girls are right there. Okay, but what you define as noise even depends, okay? Because is noise the reason why there are different heights? Maybe. Noise is just whatever you don't consider to be a factor in your model or in your data, right? So if this data were noisy, it very well could be that this is the best model, and the very simplest model basically ignores away the noise, and it's just going to say, hey, everything over here is red, ack. Everything over here is blue. After I fill in that hole. Okay. And this model might make the very best predictions because only a few outliers will fall on the wrong side of the line. Whereas this one over here that's making this rather complex surface, do you see that if the truth were this one, that one on the right would make still pretty good predictions, but not great predictions? So it's quite possible that even as much complexity as is justified by your data is too complex. So somewhere in here is where the optimal model is. And so a lot of times people interpret Occam's razor to say simpler is better, and that's kind of usually true. But I don't think that's what Occam's razor technically says. So how do you know where the best model is? basically, you take your data, you divide it into two parts, you train on one part of it, and then you adjust your simplicity parameter, then you test on the other part, and then you repeat this process 1,000 times, and whichever simplicity level produces the best accuracy, that one we say is the best. So this is called cross-validation selection. Cross-validation selection, which basically means we use an approach called cross-validation. Cross-validation is where you divide your data into two parts. You know how at the start of the assignment we divided your data into two parts? That was on purpose, or n parts. In this case, we divide it into two parts. And the reason we do that is because we want to measure on data that we didn't test on. Otherwise, you get bad results or unrepresentative results. And then you can start tuning parameters. And if you have some parameter in your model that lets you adjust simplicity, then you can find the optimal value for it.